So we'll be talking about growth rate of functions. It is nothing to do with algorithm. You have got two functions, say f and g, and those domain of those functions are natural numbers. So these are discrete functions, and then the range also is r plus, or most of the cases it is basically natural number. So in the context of algorithm, so we'll be talking about time complexity and space complexity. So time will be in terms of, say, basically number of steps that we'll be counting, which will be a natural number, 1 step, 2 steps, or 3 steps. Similarly, space also, the unit of space which will be required by the algorithm, that also will be a natural number. So we are having f and g, and then we want to see how fast this function grows. So can we bound the growth rate of a function f by another function g? So for that we have few notations. So you can see the big O notation. So big O notation says that this fn is equal to big O of gn if there exists a constant c, positive constant, and n naught, which is also positive number, such that for all n greater than equal to n naught, fn is less than equal to c times gn. So if you see the graph, so after n naught, this f is bounded above by c times gn. So we can say that g is an upper bound of f. So for example, say fn is equal to 2n square or 5n. So gn is equal to n square. So can we say that fn will be big O of gn? Whether gn will be an upper bound of fn. If you see this particular definition, so we have to find a constant c and n naught, so that fn will be less than equal to c times gn. So we have to show that fn is less than equal to c times gn is equal to n square. So for all n greater than equal to n naught, so we have to find out existence of n naught, and then this particular inequality should hold. So how do you, is it possible to do it? Yes, please.
Yes, participants.
Your fn is equal to 2n square plus 5n. So can we bound it by some c times n square?
Is it possible? You have to say.
Yes, sir. Yes, sir.
Yes. So this is basically 2 into, this is a simple one, 2 into n square plus 5 into n is less than equal to 2n square plus 5n square, isn't it? So which is less than equal to 7n square, is less than equal to 7n square for all n greater than equal to 1. So my constant c is equal to 7 and n naught is equal to 1 also in this case. So we can say that this is the case. If you see this function, fn is equal to 2n square plus 5n. So if you see the highest power is 2, that is n square. So it will be constant time n square. Basically, fn is less than equal to constant time n square less than equal to. So such a thing is, so we can write that fn is equal to big O of n square, isn't it? So let us take another example. Suppose you have a polynomial of degree k. So fn is equal to ak n raised to power k plus ak minus 1 n raised to power k minus 1 plus a0 and AK is positive. AK is positive. So what can you say? What will be the bound for Fn? Fn is equal to big O of what?
X to the power k.
Big O of
X to the power k.
n raised to power k. Can you say that? Is it true? So in fact, this is the case because if you take the polynomial, so this is a, you see the range of this function is basically r plus. So modulus of Fn, if you see this Fn modulus is basically same thing, is equal to ak n raised to power k plus dot a0 is less than equal to ak. You take the absolute value of this n raised to power k plus ak minus 1 n raised to power k minus 1 plus a0, which is less than equal to, at the most you can say that, okay, ak modulus plus ak minus 1 modulus plus a0 modulus whole into n raised to power k. It is clear? And this implies Fn is equal to big O of n raised to power k. So if you take a polynomial of degree k, then it will be bounded by order of n raised to power k. So so this is basically big O notation. And then there is something called big omega notation, which gives you the lower bound. So if you see, only thing the definition is exactly same. Only thing is that Fn is less than or equal to C times Gn. In place of that, Fn is greater than or equal to C times Gn. So Fn is equal to big omega of Gn if there exists some constant C and some n naught positive, so that for all n greater than or equal to n naught, Fn is greater than or equal to C times Gn. So suppose if I take Fn is equal to 2n square plus 5n, can I say that Fn is equal to big omega of n square? Is it true?
No.
Yes or no?
No.
Yes or no?
No.
Why no? Because if you see this 2n square plus 5n, 2n square plus 5n is greater than or equal to n square, isn't it? For all n,
Oh yeah.
right? So here I can take C is equal to 1 and n naught is equal to C is equal to 1 and n naught is equal to 1. So this definition will satisfy. So once you have a, so big omega gives you the lower bound and big O gives the upper bound. So now suppose Fn is equal to big O of n square. So can I write that Fn is equal to big O of n cube? Will it be true or not? I know that Fn is equal to big O of n square. Will it be true to say that Fn is equal to big O of n cube? Yes or no? Yeah, somebody should respond.
Yes. Yes.
Yes. So this big O upper bound, but it doesn't give you a tight upper bound. But the moment, for example, earlier case we saw that if you this function, so this Fn is equal to 2n plus 5n, Fn is equal to big O of n square as well as Fn is equal to big omega of n square. That means n square is a tight bound. So you cannot just decrease the power of n and then bound it. So it will be a upper bound as well as lower bound. So it will be more or less exact bound. But sometimes this big O notation, we know it gives a bound, but need not be a tight bound. So we have got upper bound and lower bound, big O and big omega. And theta is the notation which gives the exact bound. So Fn is equal to theta of Gn if there exists C1 and C2 both are positive and some N naught, so that for n greater than equal to N naught, C times Gn is less than equal to Fn is less than equal to C2 times Gn. It says that Fn is equal to Gn is also a lower bound. C1 times Gn is a lower bound of Fn, and C2 times Gn also is an upper bound of Fn. So it is more exact bound. So that's why we use the notation theta. So for example, if you take any polynomial, for example, Fn is equal to 2n square plus 5n. So already we have seen that Fn is equal to big omega of n square, and Fn is equal to, okay, order of big O of n square and big omega of n square. So this implies Fn is equal to theta of n square, because the big omega will give you the lower bound that C1 times Gn will be less than equal to Fn for some n naught dash, and this big omega, big O will give you Fn is equal to C2 times Gn for some n greater than equal to n naught double dash. So if you take the maximum of this n naught dash and n naught double dash, so for n greater than equal to n naught, so this Fn will be theta of Gn. So Fn is equal to theta of Gn if and only if Fn is equal to big O of Gn and Fn is equal to big omega of Gn. Is this clear? Yes?
Yes, sir.
Yes. So generally, what it is difficult to find out the exact bound, but sometimes we'll be happy with finding the more or less a tight bound in terms of big O. We'll try to find out a bound. So using this, so we know the three notations: big O, big omega, and theta. This much will be good enough. So if you see our the previous examples, okay. Okay, in this particular example, Fn is equal to 5n square plus 4n square plus 6n. 5n cube plus 4n square plus 6n. Is Fn is equal to big O of n? You tell me yes or no. Yes, no.
Theta of n cube, I think.
Okay, this is not correct, right? So Fn is equal to big O of n square. Is it true? No. Fn is equal to big O of n cube. This is correct.
The least one is correct, yeah.
This also right. So now let us see before. Okay. So if you take the adjacency matrix, so this is a n cross n matrix. So what is the space complexity for this particular input? Adjacency matrix, how much space we require? Can you express in terms of big O? Assuming that because this 0 and 1, suppose you take order of 1 space, so how much space is required for representing the adjacency matrix? Big O of
n cube.
no. N into n square entries are required by you. This is basically big O of n square, right?
N
This is the
square.
space required in the adjacency matrix. Now let us see, is there any edge I to j? So how do you check? Given the adjacency matrix, you want to reply this query whether there is an edge between vertex I to vertex j. So how much time it will take, and how you are going to do it? from the adjacency matrix, how do you know that there is an edge between I to J or not? The vertices are numbered from 1 to n, and now
Yes,
On the-
participants. So in adjacency matrix, 1 represents what? What's the significance of 0 and 1s in adjacency matrix? According to, you can give the answer. Sir is asking about that if there is an edge, then what's the value in adjacency matrix?
If there will be one, then there
so ijth entry should be 1, then there is an edge. So if A of I j is equal to 1, return yes, else return no. So now how much time does this takes in terms of big O? This first query takes how much time? Order of 1. Is this clear or no?
Could you please explain why it's order of 1?
Order of 1 means one step, because we go to the ijth entry and check whether it is 1 or not. One comparison, if this comparison value is equal to 1, then we return yes. Yes, there is an edge between I to j. If this value is equal to 0, aij is not equal to 1, then we say that it is no. So we just compare only one value. So how many steps we perform? Only one step, right?
So
Yes, sir.
will we be giving the values of I and j like?
Yeah, I and j is given to you. I and j is given to you. So in that case, you want to check whether there is an edge between I to j or not. Order of 1?
Yes, sir. Yes,
Yes,
got
sir.
it.
Acha, fn is equal to c. So in terms of big O, what will be this value? Fn is a constant function. So what will be the, how do you express this constant function in terms of big O?
1.
Big
Order
O
of
of
1.
1,
Yes.
right? Big O of 1. So if constant number 2 steps, 3 steps, or 10 steps, independent of n is the number of vertices. So that is the input. So independent of n, if we take constant number of steps, then we can write big O of 1 steps. So now take the second query, degree of I. Given I, a vertex I is given, you want to find the degree of that vertex. So how many steps it will take in terms of big O?
N.
Order of?
N.
Okay, the order of n, and how do you find? You go to the ith row and take the sum of
Yes.
the ith row, right?
Yes,
How many
yes,
entries are there? N entries are there. So
N
n
are
anyway, you want to add it. So that gives order of n addition. So order of n steps. So the third one is, what is a regular graph? If degree of all the vertices are same, then the graph is called a regular graph. So you want to check, given the adjacency matrix, whether the graph is regular or not, how much time it is going to take?
N square.
Order of n square. Because how do you do order of n square? Because you have to find the degree of all the vertices. So you find the degree of first vertex, suppose that happens to be k. Then find the degree of second vertex. If that and then you check the both are k or not. Then only you proceed to the third vertex, and all the times you find you are getting k, then it is a k regular graph. So finding a degree of one vertex, we have already seen the step 2, order of n time. So n vertices you have to find the degree. So it will take order of n square time. It's fine. Order of n square step basically, right? Okay.
Yes, sir.
Okay. Does G have a pendant vertex? How much time it will take?
1.
Yes.
Doing the same.
It will take more time. What is the not order of 1? Whether the graph has a pendant vertex or not, because you have to go to the degree first vertex and find the degree. The degree is more than 1, then you stop and go to the second vertex, find the degree of that second vertex. So while adding, you can stop once you find more than 1. But finally, it may so happen that the last vertex may be the degree 0 vertex or degree 1 vertex. So if that is the case, you have to find the degrees of all the vertices. So it will take how much time?
N square.
Order of n square. Right? Order of n square. Because suppose degree is 2, 2, 2, all the vertices. So you have to find out all the entries you have to sum, all the entries you have to sum. Finally, you have to sum all the entries of the last row also. So this will be order of n square. Similarly, does G have a full degree vertex? That means degree of n minus 1. That also will take order of n time. Order of n square time. Order of n square step. So now you are able to express in terms of bigger notation. Yes or no?
Yes, sir.
Yes. For these queries you can see. But now there is another way you can represent a graph, that is called adjacency list. We have seen, right? So how much time it will take if adjacency list is given to you? So for example, the same queries. So is there any edge between vertex I and j? So what exactly you have to do? You have to go to the ith list and ith vertex and then see the list of the ith vertex contains j or not. So how much time it will take?
Order of 1.
No, not order of 1. Order of, because for example, I want to see ed is an edge or not. This is a linked list. You cannot go directly to this place. So you have to see E, you have to go to A, then C, and then you go and then check that D is there. So you have to complete the list, because the end of the list it might be there. So this will be the length of this particular list. So what is the length of this list?
Order of n.
Order of degree of I. Order of degree of I. So these many steps it will take. So if you see adjacency matrix, this was taking order of 1 time, but adjacency list is taking order of di time. So first of all, the adjacency list is a list of all adjacent vertices for each vertex you are not storing it. So the complexity of this thing in terms of BIGO, how much space will be required for adjacency list? For vertex A, how many units you require? How many units of space require? All the neighbors you have to store, right? So
M.
for vertex 1, it is degree of 1, degree 2.
Sir, your voice is breaking.
N is equal to order of, yes, order of M. Now can you hear me? Can you hear me?
Voice sometimes breaking, sir.
Sometimes it is breaking, right?
Yes, sir. It's breaking, but
okay?
no, now okay. But sometimes whatever you are writing, it's right. Looking is a crumble, right? We are not completely seeing.
Okay,
Is
now
Sunita ma'am, is it okay? Yeah.
Yes,
Now-
sir. Yes, sir.
Yeah,
Sir,
yeah.
maybe you have network issues, so your screen is also going blur.
Yeah.
I'm just thinking that my network is not good, so that's why.
maybe my network.
But now Kavaskar voice is very clear, so maybe
Okay.
you have some network issues. Sir.
So now is it
No
okay?
problem. No problem. Yeah.
So I'm now
Yeah.
using my office this thing. So sometimes it goes
Yeah,
outside
it's
square.
okay.
Okay.
No.
So this is basically order of m space it is required, and whereas in the adjacency matrix it is going to take order of n square time, and m can be at most order of n square, so it is a very space efficient one, right? So now degree of I, given I, how much time it will take? The second query, this one. Degree of I means for any vertex is there, you find out how many elements are there in the list. So it will take order of degree of I, right? But if you see the adjacency matrix, it is degree of I, it was taking order of n time. So in this case, order of di time, which may be slightly lesser. So, and then you want to check if G is regular or not. So you have to find out first list, second list. So it is basically sum of the degrees of all the vertices will be order of m. So if you can see these operations, so it is going to take order of m time versus order of n square. This is adjacency list, adjacency matrix, right? So because of this thing, sometimes the adjacency list is preferred. Most of the time, basically, graph algorithm means you use adjacency list. So adjacency list is there, so it will be space efficient as well. And at the same time, for some of the basic operations, it will take less time. Is this clear?
Yes, participants, is it clear?
Yes, sir.
If you have query, then you can ask. Yeah.
Okay.
Yes,
So
sir, it's
now
clear.
we know big O notation and theta notation, and then for small queries, we know how to find it out. So what will be next? We are going to see. We are going to study several things. One is MST, minimum spanning tree. Then shortest path. Then matching. So these are the basically some of the algorithm. Then we have to see DFS, depth first search. And breadth first search. Right. So these are the things that we are going to study. So have you heard of something called stack or queues? Are you aware of some structure called stack or queues? Yes or no?
No, sir.
No. Okay, so let me see this one. Okay. Okay, what is a stack?
Sir,
It's a, yes, you can see now.
yes, sir, it's, but again, it's showing me blur.
Blur.
Maybe.
Maybe this is because of network thing or what? I don't know.
No, your network is fine. I think.
But you're I think you have connected with phone and laptop. Then your phone screen is more clearer. But
This
your
is-
slide screen is not clear.
No,
sir.
no, I'm not connected through phone. Only this is a Wi-Fi of IIT Delhi.
When the bar sign is white, then network is okay. When it is red, then network is not okay.
No, no, no.
Now,
For me,
now
it is fine.
now it is clear, sir. Now.
Now it's clear, right?
Yeah, you can write.
Okay. Let me see. Fine.
Fine, fine, sir. Fine.
Okay. Have you heard of something called fast in, fast out? That's called FIFO. FIFO. Stack is a FIFO. For example, if you see in the kitchen, if you put a plate, suppose this is one plate. So you want to put the second plate, where you are going to put the plate? On top of it, right? Then if you put the third plate, then you put over here. Then fourth plate, you want to remove it. So how do you remove it? You take from the front, top. So okay, so this is basically something like this. Last in, it is last in, first out, basically. Last in, first out. Okay, so this is the last element that we have inserted over here, and now you want to take it out. You want to delete it. So this is the element which will be deleted. So this is basically called a stack of plates. That is basically the English word, right? So there is a data structure called stack, and this stack, for example, if you put like this, these are the elements that you want to put in this array. So now this stack is empty. Suppose you want to insert one. That means it is basically this is called push and pop operation. Push is basically add an element to the stack. So if this stack is empty, you want to add X, where you are going to add, because this is basically top of the stack. So you add X, and the top will be now showing to the next location. This is the case, right? So this next element you want to add maybe 2, then 2 will be added. Then you remove you put the top of the stack should be like this. And then if you want to add 3, then 3 will be added over here. So in one end of the array, you keep on adding it. And if you want to remove also, remove from the same end. Remove from the same end. For example, you want to remove 3, you remove 3, and this top of the stack now will come to this location. So suppose if array is given, and now suppose it contains some elements 1, 2, 3, and 4. Suppose you want to delete 3. How do you delete 3 from the array? You know it. So you delete 3, and all the element after that, whatever is there, you just shift it to one place. So for example, this 4 will be now coming to this particular place. This is 4. So the 3 is gone, but remaining element, whatever is there from I plus 1 locations, you have to remove all these elements to one place to the left. So that is basically just arbitrary array. But stack is basically one-ended. Basically, you keep on adding from the one end and you delete from the same end. So this is basically stack where we perform 2 operations, push and pop. Now this push operation is going to take how much time? Push S to X will take how much time?
Yes, participants, answer. So if there are n cells in a stack, then how much time it will take?
Order of n.
Push means in the top only you will put it. For example, you imagine you have a stack of plates are there. You want to put a plate, where you are going to put? Yes.
Order of n or order of 1? Or order
This
of
will-
n square?
It will take how much time?
Order of n.
Order of 1 time. For example, suppose in the kitchen you have got 10 plates already kept, and a new plate is given to you, and you are asked to insert. That means you want to put this plate on the stack. Where you are going to put it? On top only,
Number 11.
right?
Yeah,
And
on
if you
top
want to remove a plate or take a plate, then you have to take from the top. So you need not have to disturb other plates. But now the plates are now put in the rack like this, right? This is the first plate, second plate, third plate, fourth plate, fifth, and this. And you want to remove these plates. So what do? You just not only remove it, all these plates, now you have to bring it one position here. So in this case, it will take order of n time. It will take order of n time in the case of array to delete an arbitrary element. But in the case of stack, pushing and popping it, pop also s will take order of 1 time. But you cannot now go and put on, for example, 4, 5, 6, 7 is there. In this in between place, you cannot go and then put the element. So only at the top of the element only you can now put this thing. This is the restriction. So stack is such a structure where push and pop, 2 operations are performed. And now whenever the stack is non-empty, you can push an element, you can pop an element. And whenever it is not full, then you can push element. That means you can add an element. So operations performed is pop and push. Operations is pop and push. These are the pop is basically delete and push is insert. This is the name in the case of this thing. So this is basically a structure called stack. And you have heard of queues? Yes or no?
Sir, here most of the participants are from algebra as well and from number theory, so maybe it is new for them.
Okay.
Maybe you can explain one more time, sir, question to us.
Okay.
That is maybe
For
better.
example, see, array you know, right? Mathematical array. Right? So this is basically a list where you can insert from one end, and from the same end only you can delete. So if you want to delete one element from the top, suppose I have kept 100 books, right? And then I want the 10th book, then what will happen? You have to remove all the elements, 11 onwards you have to remove it, 10th place you have to remove a book, and then you have to insert again and then put the stack of the books. But if you are allowed only from the top only, then if you are asked to put a book, then you can put on the top. If you want to remove a book, you can remove from the front. Such a structure is called a stack. Is this clear or no?
Yes, then some question.
Yes, sir.
No, for example, queues. If you go to the bank, in the queues where you can add new person comes, where he is going to stand?
It will be
Back.
added.
Last.
Back.
It will be
And when a
added.
person is getting served, then he will be served from the front. So, so queue will be something like this.
Added.
You have an array, but it will be two-ended, right? So suppose X, Y, Z, A, B is there. Something, this is basically front, and this is the rear. Suppose you want to add a new element, you know, this is the tail of this thing. So suppose you want to add C, then your rear will be incremented to this, and then C will be there, right? But if you want to delete an element, the front will go to this front, this will be there, and this X will go. So this addition will take place at the back, and delete will take place at the other end. So the first element that you have added will be deleted first. The last element will be deleted at the end. So it is fast in, fast out, FIFO. And this is basically also specialized kind of array where now addition is going to take place in this particular end and deletion is going to take in this particular end. So you remember, so you want to remember certain things, then you have keep on adding it, and the first element that you have added, you want to delete it. Then this is the structure that you want to use, FIFO. So then you can remove from this particular end. And this addition and deletion, this is called NQ and DQ. NQ takes order of one time, DQ also take order of one time, but the structure is such that in one end you add it and another end you delete it. Whereas in the stack, it will be something like this. It will be something like this. It will be something like this. You keep on adding element like this. So this will be a top. So keep on adding the element X, then Y, and this thing. So top will be going, and you want to delete from the top also. So this is the difference between stack and queues. Stack is basically one end only you keep on adding or removing, but in the queue, you in one end you add it, and other end you can remove it. For example, in the context of graph, suppose this is a graph A, B, C, D, E, F, G, H, I. So I want to search the vertices in the breadth wise. So A I search, and from A I go to all the neighbors B, C, D, E. But the first neighbor that I have gone, after visiting all the neighbors, I want to visit the first neighbor of A. So how do you remember that? What is the first neighbor of A? The problem is clear? Yes or no?
Yes, sir.
Okay. So I want to visit, for example, which order I want to visit? You see this 1, this is 2, this is 3, this is 4, this is 5, 6, 7, 8, and 9. In this order I want to visit. So in the graph, you are given a vertex and its adjacency, all these adjacent vertices are also there in the same row, in the adjacency matrix or adjacency list. Only that much information is there. But I want to perform this kind of search. So what kind of structure I will take? So the starting point is my starting point is A. So starting point is A. So what will happen after searching A? I will take the first neighbor is B. First neighbor that I search is B, then C, then D, E, D and E. So what will happen? I will now have a queue, and then while searching vertex A, all the neighbor B, C, D, and E I put in the queue. Right. So now I can easily remember which is the first neighbor which was visited. Which is the first neighbor of A which was visited?
First number
B.
B, is it B?
Right. So I have maintained a queue because the moment I visit a vertex, I put in the queue, keep on inserting B, C, D, E. So now I want to delete and perform the search in the first neighbor. Then where it will be there? It will be there in the front of the queue. So B, I'll remove it. And then I go to F, G, H, I. Then I keep on adding it. F, G, H, and I. So then I go to the next vertex. So next neighbor of A, that is now C. But C, now you can go, C has no neighbor, so nothing to visit. Then D has no neighbor. Then E, you remove E and E has no neighbor. Then go to F, F has no neighbor. For the left, G, H, and I. So I say that, okay, this is the order I have visited the graph. Is this clear?
Yes, sir.
So for this reason only I require a queue. Right? I require a queue. And such a search is called breadth first search, BFS. I will now show you the animation in my slides, but just you try to understand what I want to mean. So breadth first search. Breadth means once you want to visit all the vertices of the graph, you start the search at a point, any vertex, and breadth means you go visit all the vertices from A that you can visit in one step. That means all the neighbors you visit it first, and the first visited neighbor you perform the search again at first visited neighbors. So you maintain a queue, and in this queue newly visited vertices you keep on inserting, and once the search is over at a particular vertex, you delete from the queue, front of the queue, a vertex and perform the search. So such a remembering capability is required by a structure, and queue is going to provide that. Right? Yes or no?
Yes, sir.
Okay. So now the same graph, suppose I want to search like this. 1 A B C A B C D and E F G H and I. And this numbering I want to search like this thing 1, 2. If I starting from A, I can go as deep I can go as, so this is called depth first search. Depth first search. So I keep on going as far as you can go, and if you cannot go further because you have not visited all the vertices, you have to backtrack. That means you have to come back one step, and from there you go to another neighbor and keep on going this, for example. So so in this 1, 2, 3. So after 3 there is no number of F, so you come back 1. So 1 to 2 you go, 2 to 3, and 3 you come back to 2. 2 you go to another number G, and then G you cannot go further, you come back to this, then you go to H, come back to this, then I, then come back to this. At this point all the neighbors have been visited, so you come back to the first vertex and then go to the next other vertex and keep on doing it. Right? So such kind of search is called depth first search. So starting at the vertex, it will go as deep as you can, and then you backtrack. That means come back one step, and if there is another unvisited neighbor, you keep on going. So you saw the difference between this BFS and DFS. So for example, let me give one example first of all. Suppose in this graph, this is my starting point 1. I want to perform the BFS. So what will be the order in which I will go? What will be the BFS search for this particular graph? So 1, what is the neighbor? How many neighbors are there?
3.
3. So this will be 2, 3, and this is 4. Then from
Yes.
which number I have to start the search? So the moment I go to the neighbors, so this is the path I have used, these are the edges I have used, these are the edges. Then the first neighbor of 1 I have to start. So from 2, this will be 4, and this will be 5, because all the neighbors, this neighbor is already visited. Then first neighbor of 2.
Sir, we
that
should
is-
write 5, 6. 4
Yes.
is already. 5
Yes.
is already. 4 is already there, so it should be 5 and 6.
Oh, sorry. Okay, sorry. 4 is already there. This will be
5, 6, and 7.
This is 6 and this is 7. Thank you. So this is the order I can. So this is basically BFS. So DFS, if the same graph, if I perform DFS, so how should I have gone? Suppose I start the search from 1. So in the case of DFS, if you see the DFS, so what will happen? DFS, I should have gone to, as far as you can go, you keep on going it. 1, then 2, you can go to any vertex of any number of 2, that is maybe 3, any number of 3, that is 4, any number of 4, unvisited number. This is 5, unvisited number, 6, and then 7. All the vertices are there. So you are going like this, going like this, going like this, going like this, and like this. So this is the order in your page, right? So this is basically DFS, and the other one was BFS, breadth first search and depth first search. So now I have 2 options. We are going to talk about something called DFS and BFS, right? So I'll switch to the slides now. Okay, so what I said is the following. This thing is just, so this particular so this source vertex is 2, right? So BFS example is this source, this is the starting point. So this is the starting point, and
Sir,
from this, yes.
yeah, sir, screen is blur again. You just click it, maybe it will be more clear out there.
Achha.
It's clear, sir. It's clear to me.
It's clear.
It's
It's
clear
clear.
now. Okay, then maybe I have.
Okay.
Okay, sir.
But
Okay.
ma'am, it is not clear to me.
Then we
Means
both
I am
have
not
network
able.
issue.
Okay, because I am not able to see the numbers. Graph is
Are you
fine.
able to see? No.
Okay, fine, sir. Go with it. Maybe I have the network issue.
Okay. So this is the adjacency list, and then initially you make all the vertices unvisited. That means visit of all the vertices is false, right? Initialize this thing and start the search as 2. So 2, if I go, then the queue is basically empty now because you have not put it. But when you go to, let me see, it is okay. Is it coming? No. So I don't think here you will get the animation, right? So let me see the PPT. I think this is the problem with online teaching, you know. Let me see this one. Now, can you see this slides now?
Yes, sir.
Okay. So this is basically starting from 2, and then I have now put all these vertices which are now unvisited. That is, this is false only, right? The moment I visit a vertex, then I'll make it true. So next, if I go, then you can see that 2 vertex 2 is now, if you see in this table, 2 it is written T means true. I have visited this thing, and this vertex is put on the Q. That is 2 is put. Then what are the neighbors of this? So neighbor of 2 is now 4, 1, and 8. 8, 1, and 4. Right?
Yes,
Neighbor
sir.
of 2 is now, if you see the neighbor of 2, 8, 1, and 4. So 8, 1, and 4. So insert in the Q because you have deleted 2, and then this Q is now 8, 1, and 4. And those vertices you make it true. They are visited. So then if you go next one, from which vertex you have to start? You have to start from 8 because 8 in the front of the Q and 4 in the rear of the Q. So next you go from 8, you have got vertex 8, 2 is already visited, then 0 and 9. So 0 and 9. So you append 0 and 9. 8 is deleted, 8, 1, 4, the Q head. Now 8 is deleted, 1, 4, and 0 and 9 are put on the in the Q. And those of 8, 0, and 9 are now visited. That is true. Then you go to the next vertex. So 0 and 9, 9 is already visited. So then 0 was visited. So you go from 1. So 1 is 3 and 7. So 3 and 7 is now put over there. Top of the Q is 4. The next vertex you have to start with 4. So 4 already 3 and 2 are visited. So next slide is 4. There is nothing. So the next vertex that you visited is 7. 7's neighbor will be 6. 7, 1 is already visited. Then 6 is visited. And then in the Q, if you see 7 is deleted 5. And 5 was there. And then from 7 it is 6 is there. So top of the Q is 5 is there. So from 5 you try to visit because from 5 you need to visit basically, right? Okay, so then 5 and 6 are visited. So this is how this is how it is visited. So if you want to see again, so this is the from starting from 2, 8, 1, 4. So you have to maintain a queue and put all the neighbors. And then from 8 you visit, then 0 and 9 will be visited. So 0 and 9 will be visited. Then next vertex you have to visit is from the 8 is 0, 9. So next vertex you have to visit from 1. 1 you'll be visiting which one? 3 and 7. So 3 and 7. And now next vertex from which you visit is 4. So next vertex is 4, but 3 is already visited. So there is nothing. So then you start the vertex 0. 0's neighbors are already visited. So you just remove it. Go to 9. 9's neighbor is 1 which is already visited. So that also you have to remove it. Then go to 3. 3, the next vertex is 5. So this is done. This is 9. This is 3. You go to 5 and 5 to 7. So this is how you do the BFS. So is it clear, the BFS part? Or,
Yes, sir.
Yes?
Yes, sir. Yes, sir.
So that means only thing that, for example, if you have any way have gone to the Lucknow's Bhulbulaya, there is a Lucknow, there is a building called Bhulbulaya, different small paths are there. So you or maze, for example, you have seen the paper, do you know, newspaper, there is a maze problem where in one side there will be a cake and the other side there will be a rat. So then you have to find a path so that for the rat, and then rat has to find the cake at the end. So such kind of maze problems are basically this searching problem, and which are basically BFS and DFS. So this is basically BFS. And if you see the DFS, if you perform the DFS on the same, from 2, you have to go to only one vertex, one neighbor. So from 2, you go to 8. So 2, you go to 8. So this is basically 8, only one vertex. So you have to go as far as you can go to the depth, right? From 8, go to the 8 vertex, 2 is already visited, next vertex you have to visit is 0. So next vertex is sorry. Let me see this. Okay. Okay, so this was the case. So 2 you go to 8, 8 you go to 0, 0 has no neighbors. Already this 8 is already visited, so you have to backtrack. That means you have to come one step further back. So back to 8. So 8 you have to go to one neighbor. 8 list 2 and 0 are already visited, so you have to go to 9. So from 9, then you go to 1, 1 you go to 3, 3 you go to 4, 4 there is nothing, right? So you have to backtrack. 4 you have to come back to 3, 3 you can go to 5, 5 then you go to 6. So this is how the DFS takes place, search takes place. So and then so this is basically DFS. So we know two search technique: visit the vertices of the graph systematically, one using BFS, another using DFS. Is this clear?
Yes, sir.
Yes. So in the BFS, if you see, so what is the complexity of the BFS? Basically, how much time you are spending in the BFS? Each step, what you are doing it. Each one part, for example, this step to this step, if I go, no, this BFS, let's see, first of all. So this step to this step, if I go, what I am doing it? So earlier, you know, only 2 was there in the queue. So from this, you visit all the neighbors 4, 1, and 8. So if I go to this 4, 1, and 8, all these vertices are now put on the queue, right? So 2 neighbor 8, 1, and 4. You go to the adjacency list of this, and all these vertices one by one you put in the queue. That is the one step. So how much time it will take? From the source, you have to identify what are the neighbors. All the neighbors you have to put on the queue. So the queue inserting or putting, adding an element in the queue takes one order of one time. So how many how many elements of the list that you have to put over here?
3, sir.
3. That means degree of that vertex. In this case, 3. So that
3,
means
yes, sir.
degree of that particular vertex. So degree of 2, and no, degree of 2 is over, then the vertex 2 is now over, because you need not to search at this particular vertex is complete. So what will be the overall time complexity that will be required? So first vertex a degree of first vertex
Degree 3.
Where is that slides gone? Doesn't matter. So what happens when you go to that particular vertex? So this is basically degree of that particular vertex. Then degree degree of first vertex, say so V1. Then suppose this 4 happens to be V2, the first neighbor. Then I go degree of V2 plus degree of V3 plus degree of Vn, because I have to, whether all the neighbors have been searched or not, you have to keep on checking that thing, whether this is visited or not. All the unvisited neighbors I put in the queue. So this is the total complexity, which will be basically what? Order of n plus n. Because sum of the degrees of all the vertices is 2m. So n plus 2m, because n entries I am adding n plus 2m. So that is basically the complexity of BFS as well as DFS. Is this clear?
Yes, sir.
So I'll share the slides. So you have to go through. And once again, we all your doubts, after going through, I can take it up further. Okay.
Okay, sir. Okay.
Okay. So basically, this is you have to refer basically this BFS DFS. But before going to the next this thing, it's better to see some problem also. What is this? Not coming. Just a minute. Let me try to adjust it, right? Okay. So this will be fine. So this is the tube sheet that I had sent, right? Fine.
Yes. Yes, sir. Yes.
Okay. So have you tried some of the problem from the tube sheet?
Sir, not yet, sir, actually.
So we'll take it later on.
No, sir, we can discuss.
Okay, I can discuss some one
Yes.
two problems so that you can try the other problems, right?
Yeah, yes, yes.
Okay. The first problem that we discussed in the class already, right? Prove that every graph of order n greater than equal to 0, n greater than equal to 2 has at least two vertices of equal. That already you have seen, right? By pigeonhole principle. So let us try some problem that so this particular problem. So either G, what is a connected graph?
When every vertices have a path connected between them, means every vertex can be reached out. Like
No,
this.
connected means for all x, y belongs
Vertices,
to
we
V,
have a path.
there exists a path.
Path, yes, sir.
Path P x y from x to y, right? So then it's connected. So it says that either G or its complement is connected. G or G complement is connected. What is complement? G is equal to V comma E. G complement is equal to V and E complement, and E complement is equal to set of all xy such that xy doesn't belongs to E and xy belongs to V. So that means the for example, if you take this one graph 1, 2, 3, 4, if I take G complement will be what? The same what it says 1, 2, 3, and 4.
Only diagonal will be connected, sir.
The edges which are missing will be present over here. The edges which are present will not be there, right? This is G complement. So now you can see this graph is connected, but this is not connected. So so out of these two graphs, G or G complement, at least one will be definitely connected. So that is the question. So how do you go? How do I go? So let x, y belongs to V of G, right? So first of all, you see that, okay, if G is connected, so we are done, right? So we can assume that G is disconnected. So we have to show that out of these two, one is definitely connected. If G is connected, we are done, right? Because out of these two, we have to show that one is connected. So assume that G is disconnected. So what you have to show next?
And G comp will be connected.
G complement is connected. Right. So let xy belongs to V of G complement. Right. So case 1, if xy is not an edge of G, in this case, what will happen? Xy belongs to E of G complement. So this implies P is equal to X, Y is a path from X to Y. Is this clear? We have to show that given any two vertices, there is a path. So first case we took two arbitrary vertices X and Y. If those X and Y, this XY is not an edge of G, then that will be an edge of G complement, and that edge itself is a path from X to Y. Is this clear?
Yes, sir.
Case 2 is XY belongs to E of G. Right. So what is given? So G is disconnected. G is disconnected. So what will happen? This is one component, this is another component, these are the components of G. So this is my G1, G2, G3. So in this case, since XY is an edge, what can you say about the vertices X and Y? So they will belong to one component or different component?
One component.
One component. Suppose this is X and this is Y. So you choose a vertex Z in other component. Choose Z in a different component. Then the component containing X. Then the component containing X. Right. So Z will be something like this. So X to Z, there is no edge in G. So G complement, there will be an edge, and G complement, there will be an edge from this to this. So what is the path? Then P is equal to X, Z, Y is a path from X to Z. So this implies, so in both the cases, there are two cases only. XY is an edge of G, XY is not an edge of G. That is the only two mutually exclusive cases. And both the cases, we have now found a path from X to Y. In the first case, it is the edge XY. Second case, X, Z, Y. This is a path from X to Y in G complement. So this implies G complement is connected. This implies G complement is connected. Right? Is this clear?
Yes, sir.
Yes, sir.
Okay. So now you can try one more thing.
Next one, please.
Okay, next one. This one 6. So if a graph containing P vertices of degree P and Q vertices of degree Q, and P plus Q is equal to N, that means these are the only vertices. If G contains an odd vertex, then prove that every vertex of G is odd. So how do you prove? G is a graph containing P vertices of degree P and Q vertices of degree Q. Right. So if the graph contains an odd degree vertex, then every vertex of the graph must be odd degree. So you have got P vertices and Q vertices. Degree is degree of each vertex is P, and degree of each vertex is Q, right? So now suppose P is odd. So degrees, how many different degrees are there? Only P and Q. There are 2 different degrees, right? So suppose P is odd, right? P is odd. So can Q be even? So P is odd. How many odd degree vertices are there?
Odd.
Odd. Can a graph have odd number of odd degree vertices?
No.
No. Already you have seen the handshake lemma and then corollary. That number of odd degree vertices is always even. So P is odd. Then if Q is even, so even these are all even degree vertices. So odd number of odd degree vertices will be there. So the Q must be also odd. Similarly, if Q is odd, then odd number of odd degree vertices are there. So P also must be odd. So all the vertices must be odd degree vertices, and P plus Q must be even. P plus Q, because P is odd, Q is odd, both will be odd. So this will be even. So total number of odd degree vertices must be even. Is this clear?
Yes, sir.
Okay. Question number 10. Okay, there is a typo mistake, so that the maximum degree is less than equal to 6. Not equal to, less than equal to. What is the maximum degree? That delta G is equal to maximum of X belongs to B, D of X. And the small delta of G is equal to minimum of X belongs to B, D of X. So this is the maximum degree, this is the minimum degree. Small delta is the minimum degree. Now what is given is that P1, P2, Pn be n points in the plane, so that the distance between any 2 points is at least 1, that is Euclidean distance. And you construct the graph with these points as the vertices, and you join 2 points if the distance is exactly 1. So that is basically the case. So in such a graph G, the maximum degree of the graph will be at most 6. This is kindly correct in the tutorial sheet. So this delta G is less than equal to 6, not equal to 6. So how do you go about proving this? Take a vertex X. Suppose these numbers will be X1, X2, X3, X4, X5, and X6, right? So these are the numbers. So what is the distance from X to this Euclidean distance? These are the edges. So this distance will be what? You see the problem. Under what condition you have an edge between 2 vertices?
One.
So this is 1. So you take a circle, this as X as center. So this, all the neighbors will lie in where? On the circle, right?
Yes, sir.
And the radius of the circle is what? 1. So what is the perimeter? 2 pi r. So 2 into approximately 2 into 22 by 7. So this quantity is what? Less than 7, right? So that means the perimeter of the circle is less than 7. So, and then between, and then what is given? The distance between any two points is at least 1. So x1 to x2. So this distance is at least 1, at least 1, at least 1, at least 1, at least 1. And this is also at least 1. The perimeter itself is less than 7. So this distance, how many points we can put in the perimeter? At most? Yes, please.
6.
At most 6 points you can put in the perimeter, right?
Okay, sir. Yes.
Because you see the problem statement, the points are given in such a way that distance between any two points is at least 1 unit. So that is our restriction. So, and whenever there is distance is exactly 1, you draw an edge. So I take an arbitrary vertex x and I found out the neighbors. How many neighbors are there? Suppose x1, x2, x I are the neighbors. So I constructed a circle starting at x as the center, and the radius is 1. So all these neighbors will lie in the radius. Since the perimeter is at most of 7 unit, less than 7 unit. So at most it can hold at most 6 points, because the intermediate distance between these 2 points will be at least 1. So that means at the most 6 neighbors will be there for x. X is arbitrary vertex. So degree of any vertex is less than equal to 6. So the maximum degree of G is less than equal to 6. Is this clear?
Yes, sir.
Yes.
The
So this is how I
chromatic-
can.
Yeah, the corresponding chromatic number at most 7, right? Because by Brooks theorem.
So chromatic number also. So it is this
Because
kind of thing. Yes, yes.
It need not be a planar graph. Okay.
Need not be planar.
Okay.
Because the other points may be also there. For example, here it may be point, and then to this also it may be point, something like this. Right? Okay. And another thing you just see, for example, this particular problem you can see. Question number 12. If G has n vertices and the minimum degree is greater than or equal to n minus 1 by 2, then prove that G is connected. This small delta is the minimum degree. Minimum over all the vertices of the degrees of all the vertices. That is minimum degree of the graph. So the graph must be connected. Connected means there must be a path between any two vertices. So how do you go about doing this thing?
I think by the contradictions.
Yeah, very good. Contradiction. Suppose the graph is disconnected. This is a method of contradiction. Assume that G is disconnected. So at least how many components it will have? At least 2 components.
At least 2 components.
It may have more. So suppose this is one component, this is another component. So what can you say? At least one component has at most n by 2 less than or equal to 2 vertices. Right? If both are greater than n by 2, then total number of vertices will be greater than n. Right? So at least one component will have less than n by 2 vertices. Suppose 100 vertices are there, then at least one component will have less than 50 vertices, less than or equal to 50 vertices. So this is the component, and you have got total number of vertices is n by 2 at the most. So what will be the degree of this vertex? So take any vertex over here. So degree of x will be less than equal to n by 2 minus 1. That is equal to n minus 2 by 2, right? And what is given? And which is a contradiction, right? Because the minimum degree is given to be, so delta G is given to be n by n minus 1 by 2. But we have already shown that if the graph is disconnected, so each vertex in this particular component, the degree will be less than equal to n minus 1 by 2. So this condition will be violated. So this will be violated. So we got a contradiction. So the graph must be connected. Is this clear?
So for equality, we may have disconnected
Yes.
when degree of J is equal to n minus 1 by 2. Then can we have disconnected?
No, for example, that's all. We are assuming that it is, but no, what is given? Given is that, okay, degree of each vertex will be greater than equal to n minus 1 by 2. Right? So n
Yes, sir.
by 2 minus 1 is n minus 2 by 2, right? Which is smaller than n minus 1 by 2.
Yes, sir. Yes. Okay, sir.
Right? So there is a mismatch. So definitely the degree will be, of course, here you assume that n must be greater than equal to 2, right?
Okay, okay, sir.
Because n minus 1 you are talking about, right? Not 0. Right? So this is connected. One more problem we'll see, and then you can, okay. So this is an interesting problem that you should try. All of you should try this one, question number 19. This is a very interesting one. And then maybe we'll do it later on. Right? To give a try. Let S be a set of 6 persons. Any 2 persons in S are either friends or strangers. Prove that S contains 3 persons who are mutual friends or mutual strangers. Can you model as a graph? Can you model this problem number 19 as a graph problem?
Sir, handshake lemma.
Yes.
Handshake.
Say number 3.
Handshake.
Huh? So these are basically 6 persons, right? So 1, 2, 3, 4, 5, 6 persons. And then now,
sir,
yes?
is it coloring problem? Coloring the graph?
Not coloring. So for example, see, I'm just modeling it problem. Say. So any 2 persons are friends. If it is a friend, you draw an edge. Right? So these are friends, right? So the friend is basically a relationship. So whenever they are friend, you draw an edge. And when they are enemy, means there is no edge. So it says that G in G or in G complement. G complement means all the strangers will be an edges. There exists a triangle. 3 mutually friends or mutually strangers. So there exists a triangle. Right? So this is an interesting problem in the sense that this is the basis of Ramsey theory. Have you heard of Ramsey numbers? Right? So this problem can be modeled as that once you take each person as a vertex, and whenever there is a friend, then you draw an edge. So in the complement, what will be the edges? Whenever they are strangers, these are the strangers, and these are friends. So whenever they are strangers, in the complement there will be an edge. Whenever they are friends in G, there will be an edge. So three mutual friends means in G there will be a triangle. So it is the mutual friends means this is a triangle. In mutual strangers means in G complement there will be a triangle, right? And 6 is the minimum number. If you take less than 6 people, then such a property will not hold. So either G or G complement will contain a triangle, then minimum number of vertices must be at least 6. That is basically Ramsey theory. So you need to show basically that either G or G complement G, you have a 6 vertex graph, any graph you take, either G or in G complement there is a triangle that you need to show. All right.
Yes, sir.
So that I have not completed. I have just modeled it. So now you have to complete it, and maybe later on we'll see, because this leads to an important theory called Ramsey theory.
Yeah.
So that's why you should give a try first. Okay.
Okay, sir.
Okay. So let us take one more problem and then we'll stop. Question number 23. I'll give you a hint and then you try to complete it. G is a graph of order 3n. So number of vertices is 3n, and then degree with degree is equal to degree set of G is equal to n, n plus 1 and n plus 3. 3 type of vertices are there, right? So degree n vertices are there, degree n plus 1 vertices are there, degree n plus 2 vertices are there, and total number of vertices in the graph is 3n. So you have to show that G contains either at least n vertices of degree n, or at least n plus 2 vertices of degree n plus 1, or at least n plus 1 vertices of degree n plus 2. Right? So, okay, this is extra thing. This is extra thing. So how do you show this one? So method of contradiction. So that means all the 3 conditions are false. So at least n vertices of degree n. So what if it is? What is the negation of this?
At most n minus 1 of degree n.
At most
N minus 1.
n minus 1 of vertices of degree n. N minus 1 vertices of degree n. Second thing, at least n plus 2 vertices of degree n plus 1. How many? N plus 1 vertices of degree n plus 1. And third one, negation, at least n plus 1 vertices of degree n plus 2. So n vertices of degree n plus 2. Right? So if all the 3 conditions are not satisfied, then n minus, at most n minus 1 vertices of degree n, at most n plus 1 vertices of degree n plus 1, at most, this is at most, right? At most of degree, these are degrees. These are number of vertices. So how many vertices are there? At most means less than equal to. Less than equal to how many vertices? If you add these 3, then you will get how many?
3n.
3n. So since at most means less than 3n, but total number of vertices is how many?
Equal.
Exactly
Yeah.
3n. So this will be exactly, right? This will be, all these things will be exactly. Exactly n minus 1 vertices of degree n. Exactly n plus 1 vertices of degree n plus 1. Exactly n vertices of degree n plus 2. So now you just take case 1. N is odd. And case 2, n is even. If n is odd, then what will happen? N is odd. So n is odd. So n plus 1 is even, n minus 1 is even. So n is odd. So n plus 2 also is odd. So odd number of odd degree vertices. Is it clear or no? Suppose n is odd. So in this graph, which are the even degree vertices and which are the odd degree vertices? N plus 1 is odd. So n is odd. So n plus 1 is even, n plus 2 is what? Even. So n plus 2 is odd and n is also odd. So how many are there? First and second, these are odd degree vertices, and these are odd degree vertices. So how many you have odd degree vertices? 2n minus 1. Yes?
Odd number.
N is odd. So now see, n minus 1 vertices of degree n, n plus 1 vertices of degree n plus 1, n vertices of degree n plus 2. When n is odd, which degrees are which one? N is odd and n plus 2 is also odd. So this is odd and this is odd. So how many odd degree vertices are there?
2n minus 1.
2n minus 1. So whatever
number.
n you take,
Odd
2n minus
number.
1 is already odd. So
Odd
odd
number.
number of odd degree vertices. So you got a contradiction, right?
Yes, sir. Yes, sir.
When n is even, n only n plus 1 will be odd, right? So n is even, so this will be odd. So how many odd degree vertices are there?
Odd number of odd degree.
Odd number of
Odd degree.
odd degree vertices. In second case also, you are getting
Get a
a
contradiction.
contradiction. So at least one of the condition must be true, right? So the problem looks difficult, but once you attempt it and then what method you are going to use it, after that it becomes easy.
Easy.
So yeah, so you just go through the other problems, and maybe the another tube sheet I'll send it, and then we'll discuss. So only way to learn is basically solve the problems. And of course, I understand that the algorithmic part is slightly newer, but assume that, okay, there is a concept of DFS and BFS. How it is done, you can read it later on, but DFS can be done in order of n plus 1 time, and BFS also can be performed in order of n plus m time. Right.
So both are searching the spanning tree, right, sir?
Yeah, both will give you can search the vertices. So suppose you want to see the graph is connected or not.
Okay.
Suppose I perform BFS or DFS. Using that, can I test whether the graph is connected or not? For example, the graph is like this. So if you perform BFS at this vertex, where it is going to stop? It will stop over here, 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 and here, right? After that, these vertices will not be searched. Yes or no?
Yes, sir.
So if starting at one vertex, if the BFS or DFS is performed and all the vertices are searched, visited, then only graph will be connected, otherwise not connected. So it will prematurely stop. So after visiting this thing, it will stop. There is no vertex to search, but number of vertices visited, you can count it. That is not equal to n. You declare that the graph is disconnected. So this is a byproduct of BFS and DFS to test whether the graph is connected or not. Right?
Okay, sir.
Okay. So tomorrow lecture we'll see some more applications when how to use BFS and DFS to test other properties, and then we'll talk about trees and then spanning trees, spanning tree MST algorithms. That you don't require more of algorithmic notation. We'll be able to understand what is minimum spanning tree, and then I'll talk about some problems also. Right?
Okay, sir. Okay.
Okay. So feel free, whatever questions you have, you ask, and if you are not able to understand something, just let me know. Basically, I'll go slow.
Yeah, you can use the full board, sir, because the half is one is the presentation,
Okay.
the other one.
Okay. So you are not able to see properly.
No. So that is so both we cannot see it simultaneously. So that is the thing actually. Yeah.
Okay. So you should have to. So this kind of thing, then I'll use.
No. See, this is very big, sir. So see, writing pad is only writing pad is the.
This much is okay. So for example, this you can see.
Yeah. So everything we are seeing, sir. But the full screen, if it is there, so I think you are zooming, right? You are zooming.
This becomes bigger. Yeah, this is the problem with something online, and I am also new.
Yeah. That may be. I also heard that.
Okay. I think today we'll stop over here.
Okay,
Sunita?
Sunita,
Okay, sir. Okay. Thank you so much, sir, for nice lecture.
I'll send the slides of today's lecture. Maybe.
Yes, sir. Yes, sure.
Okay.
I will share.
Okay.
Okay, participants. Thank you so much for attending, for being with us. Thank you so much. And
ma'am.
please ask your queries if you have. Okay. Sir is always here for solving your queries, and me also. You can send me if you have any query, then you can send me on WhatsApp as well. Okay.
Okay, okay. Okay, sir. See you, sir. So see you
Okay.
tomorrow.
Okay.
Okay, madam.
Okay.
Yeah.
See. Okay. Okay.
Thank you so much, sir. You can
Thank you.
unshare your screen. Yeah.